Hello everyone, welcome to the December edition of CAIS seminar. Today it's a pleasure to introduce Dr. Katarina Grolinger. She's an associate professor in ECE, Electrical and Computer Engineering at Western University, and she's also the director of the Software Engineering program. She holds a Canada Research Chair in Engineering Applications of Machine Learning, and she's a faculty affiliate at the Vector Institute. Her work sits at the intersection, and you will correct me if I'm wrong in any of this, of AI systems and sustainability, with a strong focus on applying machine learning to real high-impact domains. We will see an example, or more than one, today. She will talk about how modern AI, when combined with building physics and responsible data practices, can help accelerate the transition to low-carbon, resilient built environments. So this is super interesting. We're very happy to have you, and the floor is all yours.
Thank you for a great introduction, and thank you all for being here. So, to talk a little bit more about what I do, so numerous things were already mentioned. My research is on different applications of machine learning. So I don't do only energy or only sustainable cities. As my CRC chair is engineering applications of machine learning, I cross the different areas, primarily around sequential and time series data. Today, we're focusing on the AI for energy. It's sustainable and smart communities. So what some areas of how we use the AI to get to these more sustainable and smart communities. Obviously, my research is funded at the diversity of Canadian funding agencies. I work a lot with the industry partners. Large part of my work is funded with the industry partners, and we have some of them over here. A lot of today's stuff is in collaboration with the London Hydro and Utility Smart Corporation. So the two are in the area of energy. Obviously, distribution company and Utility Smart, they manage data for utility companies. They don't do it particularly for London Hydro, but they do it for other utilities. I do a lot of cross-disciplinary work, and some of this today is cross-disciplinary. So obviously I do AI, but I collaborate with civil engineer, power system engineers, and so on. So why do this AI in an energy thing? Here we have some numbers. Electricity is rapidly growing. Yes, we have these more efficient devices, but the problem is we just have more of everything. Cities are bigger, population is growing, so overall electricity is going up. And you can see a plot over here how steeply it is growing in recent years. And we are doing energy savings activities, but we are not compensating for that increase in digitalization, in electrification, and so on. So why is that a problem? Energy production is the largest source of greenhouse gas emissions. 75% of global emissions come from energy-related activities, either using energy or producing energy. So we need to be really careful on both sides, how we are using this energy, but even producing energy will cause greenhouse emission depending on how we do it. So why the buildings? A lot of my work is around energy and buildings, so why focus specifically on the buildings? They are 30 to 40% global energy use, depending on different sources, you'll find different numbers. They're the largest sector for electricity demand. If it's a larger sector, then we have a possibility for the highest impact. 37% of CO2 emissions come from the buildings. So really high impact of buildings on our environment in general. Opportunity, it's a big problem, but it's a big opportunity. By doing something in this sector, we can improve our environment. With the building, very specific things to the building is we don't just swap them. On AI, we swap our servers every few years. So if it's not very good, hey, we're gonna get rid of it in a few years. Buildings, more than half of existing buildings will exist in 2050. So we can't just leave them the way they are. We need to improve them through retrofits and so on. And we need tools to do this in a better way. And to do these tools, we can use machine learning for some of it. So when we talk about energy and buildings, there are two main streams of the energy modeling. One is the AI and machine learning modeling, and one is physics-based simulations. So the good chance is that we don't really have anybody in this room that's familiar with the physics-based modeling. So what this really is, it would typically be done by civil engineers. So they would make a model of the building, including the size of the building, the window, the shape of the building, what is the insulation in a building, what kind of glass it has, and so on. That model that runs simulations, and the simulation is based on physics principle. How much energy is lost through the windows, through the walls, through anything that's in that building. So this is typically done by civil engineers. So an example is the Energy Plus. You can see one example of the building done into this.
So I worked a little bit with a project where they were doing physical simulation, but it was a PhD project in architecture. And their goal was to build a simulator and make sure that, let's say if it's a hospital, the doctors they have it wide enough hallways, right?
Yeah.
So it seems like the engineering layer comes on top of the architecture layer. So can't I make design choices on the architecture layer that would over-constrain the engineers down the line? And that,
yes,
I designed it to be, yeah.
Definitely. So the two need to blend.
Exactly.
If you want to make really efficient building, let's just not put the windows. It's going to be more efficient, but we can't do that. It has to blend both of it. Or you mentioned the hallways. More hallways we have, they're more inside, so you could increase energy efficiency, but you can't look at one or the other. It has to do both sides.
So it's simultaneous.
Here, I'm more focusing on simulating for how much energy this building would use. Of course, the design needs to accommodate other things, but we want to reduce the energy. So what is great about this modeling, this is done before the building is built. And we can explore what if scenario. What if we change this? What if we change that? This is great for that. The problem is you have to have detailed physics of the building. You have to have the model of the building. So this one here, you have to know everything about the building. Often it's not available. Also, these models, when done before the building is built, often will give lower energy than was real when the building goes into use. Because it's hard to predict how the building will be used. And if we do perfect design for the building, if in summer we put AC on a 15 degrees, it's going to kill electricity. So it's the use of the building. So it has advantages, it has disadvantages. On the other hand, we have the AI piece. It learns from historical data. So we typically do historical data plus some weather variables, maybe some additional stuff related to use of the building, but based on the historical data. So what that means is we have to have that data. If we have this historical data, AI will get much more accurate solution than a physics-based. But we don't always have that data. We don't have the data for new buildings. So there are some tricks to use other buildings, but in principle, we need data. Cannot carry what-if analysis. If the building is used the same as in the past, AI is great. But with AI, typical modeling, we can't do, what if something changes? because the AI just learns from the data. If the building changes, AI will degrade. So AI has its own disadvantages, but if you compare the two, so AI cannot be done for new buildings, this one can. AI cannot carry what if, this one can. And if you look the opposite, this one can scale much easier, doesn't require detailed information, this one requires detailed information. So there are advantages and disadvantages are kind of opposite. So the question is, can we merge these things to make better models that will take advantage of the both? What is difficult with this side is, for example, I work in AI ML. I don't know how this tool works. I don't know how to model the building. So it requires the interdisciplinary approach. And they're very, very different techniques. So that being said, this talk will go into three directions. The first one is just focusing on AI building energy modeling. So what are some latest things we did in energy prediction for the buildings? And we'll do the hyper networks, Kolmogorov, Arnold networks, and federated learning. So federated learning is really to promote the data ownership component. Then we'll go AI-driven building optimization. How can we use the AI to optimize building design? And the final one is integrating physics modeling and AI to get a better predictive models. So when you talk about AI in building energy modeling, it has been around for a very, very long time. So it's kind of a little bit old topic. There were recurrent neural networks, LSTMs, CNN transformers, and so on. They get great accuracy. Still, it's difficult to capture those variations in energy use. Also, most of the studies would pick an office building or a school or apartment building, so single building. So if we design the AI that's for single building, if we retrain it on a different building, is it really going to work as well? There's very limited work in that area. Also, privacy and data ownership. So with AI, we take data from everywhere, put it on a single computer, and we do the training there. A lot of privacy concerns because we are sharing the data. And there are big privacy security risks with that sharing. So what my research has done is kind of I'll cover just high level on three main directions. The first one, hyper networks and CAIS. They're really to do just a more flexible modeling. And we'll see that they are really getting better results than these ones. Another advantage of these CAIS, they're not black boxes, they're explainable models. We didn't analyze explainability, because when we did this work, there was no CAIS for a time series. So we needed to design these kind of models for the time series. And then federated learning for the privacy support. So the hyper networks, in general, there are these networks that generate weights and biases for the primary network. So you have two networks. One is the hyper network, and the other one can be anything, can be LSTM, CNN, whatever. The primary network doesn't get updated through backpropagation. It's the hyper network that provides these weights. They're typically used with feed-forward neural network. So when we did this work, there was no LSTM or RNN-based network that was specifically for time series data. And you'll see majority of the work that I talk about today is from 2025. So the papers that relate to this work, they'll be showing up here. So our hyperenergy, so we call it hyperenergy because the hyper network is generic and ours is specifically for hyperenergy. It integrates with LSTM, and we added additional components, the polynomial and LBF kernels, to improve performance. So here we can see the overall structure of our hypernetwork. So the first component is the hypernetwork itself. So the hypernetwork gets the inputs. So in our case, the inputs were historical energy used. We generated some variables such as a day of a week and I don't know, hour of a day, so on. For some of these works, we integrated weather. For some, we didn't. It doesn't change the approach itself. So the hypernetwork is the fully connected network. Relatively simple. It gets these outputs, and it will provide, as output, it will provide weights and biases for the primary network. So outputs are weights and biases. Then, from these weights and biases, we have to restructure them to be able to push them to the primary network. Then, we have the primary network that receives these weights and biases. In our case, the primary network is the LSTM. Before we did this, the hypernetworks were just with the feed-forward neural networks. What is very specific here is that weights and biases in a primary network, they are not updated through the backpropagation. They are received from here. They get the weights and biases from here. On the other side, the weights and biases here are updated through the backpropagation. So yes, we calculate our normal loss, whatever loss function we calculate, but it is the hypernetwork that's gonna get updated and not the primary network. And we have some learnable adaptive kernels that we put in the front to further boost the performance. And here are the results. With this work, we specifically wanted something that's going to be very good across many use cases. Yes, we still train the network for house 1 separately, house 2. And to prove that our work consistently works on diverse consumers. So you can see SMAPE, so mean absolute percentage error, it's symmetrical just to get rid of divide by 0. Errors are large, 37, 21, 29, 37. Is this larger than in literature? Yes, because literature picks up schools, which are really easy to do. And you can see a number of other algorithms, and our approach is lower error than all of these other algorithms. So in this case, house 3 was a house with EV charging. It's a higher error than this one, but you can see house 1 and house 4, very, very high errors, because they have very random, there's no firm patterns for them. Mm-hmm.
So in the previous slide, there's a separation of concerns kind of, right, between the left side and the right side. So the right side is just fed and used as a calculator, or does it also provide the feedback to the when you train the when you train the left hand side? So
you mean
could I replace it with an ARIMA model on the right hand side?
Could you do ARIMA here? I'm not sure if you could, like, I could see this being redesigned for a variety of networks to, instead of LSTM putting, I don't know, CNN or transformer or something. Right away, I don't know. Like,
so ARIMA is P plus K parameters, and all it needs is to communicate the y hat, right? I mean,
this piece, the primary network, gives as output prediction. So ARIMA could give you prediction, yes.
Right.
So then from this prediction and from the actual values, you calculate the loss, and then this piece is updated.
Right.
So if you are doing this as ARIMA, the question would be, what should be the outputs here to push it to ARIMA? And right now, I don't know from top of my head what would exactly that connection be, but this could be replaced with something else.
With the explainable.
So this is around the houses, big areas, and here is about on different buildings: manufacturing, medical clinic, store, and office. So now, medical clinic, 2%. It's the same approach. Previous slide, we were talking 37, 21, 37. Same approach. On the medical clinic, it's 2.42. The reason for this is medical clinic and office, they are very fixed schedule. Their thermostats are very set, very fixed schedule, firm patterns, so we can get a great accuracy. In terms of SMAPE, our model is better for manufacturing and medical and retail. For the office, attention LSTM gave slightly better results. So if we are doing only one specific building, could potentially something else be slightly better? Yes. But overall, when we look at houses plus these different buildings, our approach overall gets the better results. So we did this study and got a great results. Around that time, these Kolmogorov-Arnold network came about, and we were looking at to them, would the energy forecasting benefit from those networks? So CAIS were introduced as alternatives to multi-layer perceptome. So it's alternative to fully connected network. They don't have a linear weights. Instead of weights, there are spline functions that are parameterized and they are learned in the training process. So this kind of design makes them very flexible. But the problem is they don't consider temporal data. So the original CAIS, they were not considering temporal data. You couldn't do time component. So then we decided we're gonna design our Kolmogorov-Arnold recurrent network, so CARN, so recurrent model, that takes inspiration from recurrent neural network and from the CAIS. So we take that CAN theory and we put it together with a recurrent structure. We design these temporal bases and temporal spline functions. So now we don't have that traditional activation function that just apply, I don't know, ReLU on some of the inputs or something like that. We have these approximations through the splines. So how does this look? So again, this was published just this year. How does this look? So if you look at this picture, if you're familiar with recurrent neural networks, either LSTMs or RNNs or GRUs, this looks a little bit like it, because we need to integrate these time steps. So from here we have the previous time steps, And this is the core of our system. So we have three main components: temporal basis function, temporal spline function, and memory mechanisms. So the main splines are in this area. So we have the B splines. They are running on the grid. So we have the grid, and these B splines approximate according to that grid. Finer the grid, better the modeling, but the more computation is involved. These B splines, they are learned during the training process. And then we have the weights, and they get put together. And you can see that both this and this gets the current value at the current time step. So here we have splines, and we have here just the C loop or squish function. Then we're putting these two together in this memory mechanism. So memory mechanism is putting these two together, and it's taking previous time steps. So we are having that recurrent thing, the way that RNNs or LSTMs have. So it's this component when it's getting previous time step. So it's our memory mechanism that combines the portions from CAN networks plus the LSTM. And then at final, we are getting the predictions going into some future time steps. Again, we are doing large-scale experiments on numerous use cases. With this one, we only compared it with the recurrent networks, RNN, GRU, and LSTM. And our current is the last in a row. Why only these three? Because they are kind of counterpart of our recurrent structure. So all these ones are recurrent structures. The first three are, I will call them traditional recurrent neural networks, and these are the spline. Ours is the spline base. Does this get better result than hypernetwork? No, really, hypernetwork still gets a better results. Where this is powerful, these are not the black box models anymore. We didn't go into analysis of their use with respect to explainability. We more went into, can this be done for energy? Can we achieve reasonable results? And they are quite close to the other recurrent structures. If you look at these numbers, so for the house 1 and 2, our current is better. For the house 3 and 4, depending on which metrics you look at, ours is, from here we can't say that ours is better. Still, it's comparable accuracy, while it has other advantages. And in this case, again, we're doing same houses as a previous study. Scenarios like this are very difficult to capture. The blue is a tuning, hyperparameter tuning, and the red is testing. This is very different than this. So, yes, these relatively high numbers are expected because of the data structure. And then we are doing different, more buildings. Residences, these are 2 residences on campus. Again, ours is comparable, not better. And the same on manufacturing and medical clinic. So the conclusion for this work, yes, we can use CARNs, we can do it. It gives solid results, not necessarily better than the other. But if we need explainability, the CARN is explainable because we're not using traditional activation functions. And here is just a graphical representation. You can see that for residences, all the models are really good. For the houses, they get weaker And then for the manufacturing, clinic, store, office, they can get better. They're not too far from each other. So Karn gives comparable results for these.
Can we say that when a pattern of the building is like more random, Karn is better than LSTM? Or, yeah, 'cause like,
So we
like
know that the
outdates or-
patterns here, we know that these 4 houses, their pattern vary more than this. Still, like here, I can't say that Karn is better because RMSE for LSTM is lower. It's close, but I can't claim this is better. And the figure, like here, they're so close. This is specifically SMAPE, while in the table we have other metrics. We compare on SMAPE because SMAPE we can compare across the buildings. RMSE we cannot, because RMSE is a scale base. That's why we don't have graph for the other metrics. Was another question?
So were you comparing also against the first approach you've shown us, or is this just a generalization of it? 'Cause
So
that
we
was
did,
yeah.
they're the same houses we did in the other study. The hyper networks are better than
And
this.
this is not a hyper network, it's
No,
it's
this
an
is
extension
a
of
totally
LSTM.
different, this is this Karn network
Yeah.
that are step away from our traditional neural network. And if I remember correctly, these CANs that this was based on, if I remember correctly, this was introduced in 2024, if not even 5. Like, these are very, very recent. They're alternatives to the multi-layer perceptron. Their great feature is that explainability. And I could see, and even after we did this one, I think this came early this year, there's more and more CAN networks that people are
Sort of
doing
like,
because of this advantage.
So sort of like GANs, but neurons.
So GANs are,
It's blind, right?
GANs still use the activation functions similar to regular networks, so they're still not.
Sorry, I meant GANs. So
Oh, the CANs, our CAN adds that recurrent part
Yeah.
to the original CANs.
Can I ask one more thing about this pattern? Exactly. So your models are more for design time problems, right? You're not trying to predict it in, what's going to be tomorrow's.
No, it is what's gonna.
You can, but what's your primary?
I think it's a 24-hour ahead. So use previous, I don't know, X number of days. I think it's 24-hour ahead.
But typically, would they be used by electrical companies to predict tomorrow's surge, or to design buildings for the long?
So this first part would be used either by the companies to plan for the loads, or people to plan for their energy consumption.
Buildings.
This is not for the building yet. So used for building optimization, this is coming. So this is more of a energy management as
Rolling,
opposed to the
horizon.
design. Yeah. I don't remember how far ahead we did these ones. It's all in the papers. Sometimes we do. Typically we have 24 hours because that's what's typically needed for utility companies and distribution.
Yeah.
But sometimes we add like a 1 hour or 6 to have a further
Yeah.
evaluation.
If you can go to the pattern slide, my point is that you can sometimes select the training to be shorter term, right? Because of this use, you don't need to use the entire training session potentially. That's what we see when we.
So we use this entire
thing.
green thing
The
to
entire
train it. Yes, and the blue thing to
Validate.
optimize hyperparameters. And the problem that this is so different here results in high errors. So another thing is, with this, all these things put the data onto a single machine. So that's a problem. You collect data from numerous sources and you have to share them. So you're creating network traffic, you are causing issues with privacy and security. So federated learning has been very active in recent years because you don't transfer the data. So the data can sit whatever these nodes are, computers or whatever they are, and learning happens on these nodes. Only the parameters are shared with the server, and server aggregates that knowledge. So we can, with the neural network, we can say that weights and biases are where the knowledge is. So it's either weight or biases or loss that is shared with the server. And server does aggregation of that knowledge. These methods work amazing if your data is IID data. So if your data distribution on these nodes is similar. But if you're dealing with the non-IID data, so if the patterns here are different than patterns here, then here, and distributions will be different, federated learning has a problem. So the main algorithm in federated learning is the Fed averaging. And it's kind of go-to approach. It gets great results for IID, but it fails with the non-IID. So what happens is each one of these ones goes to local minimum as opposed to global minimum. Also, a lot of these works assume that all these nodes in a system are always available and that they're always giving back the results, that they're synchronous. That is not realistic. We would have asynchronous parts as well. So what we did, we designed this Fed norm. So this work is a little bit older, from 23. So this Fed norm assumes that these clients have a different computing capability, assume that some of these clients will come offline occasionally, more like a real world scenarios where not all of them will always send stuff back. So at the time T0, the server shares the stuff with all the nodes, but the updates, so maybe from the first node, updates arrives at T1, from second node and T2, and so on. In this approach, if we try to apply traditional Fed averaging, it will cause problems with the convergence. So to accommodate for this, and to accommodate the non-IID data, so different distributions, we created this Fed norm. And this is the basic idea on how Fed norm is merging knowledge from different clients. So you have a number of clients, and they send the stuff to the server at different time spots. So Fed norm measures similarity between global and local model. So that global model and the local, how similar are they? So that's one measurement. Then what is direction of the change? So maybe global model wants to change the weight up while the local model wants to change down. So we need to figure out that direction. On the top of that, we are adding Gaussian function to reduce skew towards large values. So this is just to handle the large values. And finally, the softmax to calculate participants ratios, because we want those participants that are moving in the same direction to have a higher impact. So by doing this thing, we are ensuring that our convergence improves in spite of models having, instead of nodes having very different data. I don't go into equations and direct details on the calculation, but this is the basic idea around it. Here is the data that we run it on, a sample of data, and you can even just looking by this, very different patterns. So we can see that it's a non-IID data because all these nodes are greatly different. And there is the comparison. Here is our Fed norm, and here is the number of other algorithms. There is the traditional Fed averaging and Fed FDG, and there are different adaptive algorithms as well. And we have 8-hour ahead and 16-hour ahead forecast, and our approach was better than these other algorithms. So we have shown that, so our approach is better for this kind of data. If we have IID data, the difference between the algorithms will be much smaller. But we were specifically interested for scenario where we have asynchronous and non-IID data. And in general, a lot of federated learning work is to enable handling non-IID data, because that is a real-world scenario. So all these stuff that I talked about, prediction, all this, that was done in collaboration with London Hydra. And the final slide on this federated learning is convergence. You can see rounds, global rounds here. You can see the error in hours drops very quickly, while some of the algorithms have problems. Fed averaging, not too bad. It takes a little while, but it stabilizes. This one has spikes, and this one you can't even say that it converged. So overall, our approach was better than other federated learning strategies.
Do we need to update, upgrade the meter to do the calculation, or all the training is like on an app?
Sorry, come again?
Yeah. Do we need to upgrade the meter to do the calculation, or
so
in the app?
we did. If you would really want it on the meter, it would need a different device. With this one, we were more assuming more looking into the computation perspective. Can this approach, can federated learning even get us? Because at the beginning, we were very concerned. Can really one model be built for all these ones? They are very different. And yes, it can, and the overall results were good. We were more interested on the computation side. But yeah, you're right, the meter would need to be different. So this so far was around just the AI to do the modeling and prediction. So now you're moving to the AI for building optimization. So when we design the buildings, the way it typically works, we design it in something, and it doesn't have to be, we're doing Energy Plus mostly. Energy Plus is for simulation of energy. Often these buildings are designed in something else and then transferred to this. So the way it works, they put this model into the Energy Plus, and then they run simulation. It can give you, let's say, hourly energy consumption. Then they would go back, they would change the walls, let's say this isolation in the walls, run it, let's see what's energy consumption. Change how many windows are there, look at energy consumption. So that's a traditional way. Outrageously time consuming. Very, very slow because they need to run like thousands of simulations. So surrogate models are really these models that are replacing Energy Plus runs. But to build them, we need data. The way it typically works is we have identify objective, what are we interested in, and then we have design and simulation of building performance. So this part is traditional. So we would run still traditional one, maybe for like a 50 or 100 runs, limited number. Then we would use this one to train our surrogate model. Once we have this model, then we keep changing inputs to the model to explore design combinations. Because this model is already trained, this inference component here, optimization with with surrogate is very quick. So yes, training this is slow. But comparing to the time to doing this process versus only taking the, I would say, old style still is incomparably slower. The point is, training this is slow, but once we have that model, this is very quick because model is already trained. So there are numerous surrogate models out there. Most use feed-forward neural networks, but there are some variants on that. There was like one or two works that used reinforcement learning. So we were interested to see if you're using reinforcement learning, can these things be transferred between the buildings? Because this traditional approach, you have to do it each building, each location individually. Design the building, do the simulation for a specific location to account for specific weather. These surrogates, the same, for specific building, specific location. So we were interested to see, can we transfer this between the locations and between the buildings? So in this case, we're doing reinforcement learning. So we have a surrogate. So this surrogate here is the same as what other people are doing with the surrogate model, but for us, in reinforcement, this is going to be in environment. So in reinforcement learning, we are getting feedback from environment. We do the action, and there is some feedback telling us, is that action good or bad? So this is this environment that tells us, is the action good or bad? This is our reinforcement learning agent that works together with this surrogate to explore the design space and come with optimal design. But we wanted to know, if we build this on one building, can we move it to a different building? Initial results were published, but the published results are very limited. We have another work that's under review that goes more on this optimization and transferability. And here we have reinforcement learning. Here is if we have a building in London, medium-sized building, and we do transfer learning to the same location but large building. So blue is with transfer learning and red is without. So yeah, transfer learning is better if we are doing this transition. This is same building size, medium, but going London to Toronto. After a while, with transfer learning is better. And there's a couple more combinations. With this one, without transfer learning, the reward is dropping. So transfer learning for this one didn't work pretty much at all.
So do we have something like ground truth to evaluate, I mean, not like in real life, but in actual, whether this decision is going to be either good or bad, or we can only have this comparison between different algorithms?
So, good or bad in real life, I would say it depends on what you want to do with it. So this one, I don't think it's, this is from this specific publication. This work in that publication, it's not close to real life yet. But we want to move in that direction where we can be reusing these models. So the goal is eventually we'll get this better and we're going to be able to review it. But with the real life, if you think about previously, we had predictions for school that are 2 to 6% accuracy. That's a good prediction. It depends on what you want to do this. There are numbers showing on the utility level. If the utility level is able to increase accuracy for, let's say, 1% increase, there are massive savings. I don't remember from top of my head what are the numbers. I know we use them as a reference, but they are getting savings in millions. So it depends on what you do with it. For the individual homes, we have high errors. But if you are interested, we are doing it on all these, we are doing it hourly, so how much is for that hour? If we are looking at the daily prediction and comparing daily level, errors would be much lower. So that, for example, with house with EV charging, that would be, yes, the accuracy is not great for hourly, but it's solid on a daily level. So that can be used for planning a grid, because the grid has to support a certain number of EV houses with EV charging. And that's there we are more concerned with daily or the spikes. So it depends on the specific use case. So now I'm coming back to, we have seen this before on physics and AI integration. So I'll talk about merging it. So there is a lot of work there on the physics-informed neural networks, where you would take some physics equation and you would merge it with the neural network. That is the way that we wanted to go about when we started this. But the problem was, in this energy plus, there are hundreds of equations. We don't understand them. We're not building engineers. And the building engineers explain it to us, but we can't integrate hundreds of them. So we decided, why integrate equations? Why not take the power of this energy plus and put them together? And this is how we have done this. So we have the physics-based model and we have the deep learning model. This deep learning can be the hypernetwork or CAN or LSTM or anything. This physics-based can be energy plus or another model. They're providing some outputs. It goes in the parallel projection. We have the memory unit and the memory experience module. So these are really a different calculations similar to what we have in neural networks. Some multiplications, activation function, weights, and so on. At the end, we are getting the energy consumption. So you can see that input is output of deep learning and physics, and this structure is learnable. So it learns how to merge physics-based with the deep learning-based. This shows what examples of scenarios we wanted to look into. So for example, this scenario assumes that both are available, deep learning and energy plus. This one assumes there is no energy plus model. So the system has to learn only from the deep learning. And then we have the partially missing as well. There is no partially missing for energy plus, because energy plus it's either all or nothing. We have done this in collaboration with the civil engineering department with building on a campus. So they did this model of our campus building, and this is done in energy plus. This is one of the residences, and they can simulate energy consumption using physics-based model energy plus. Don't ask me how details on this one, because I don't know how they build the energy plus model. What we do is we're going to take this and put it with the machine learning.
Can you say if it's a discrete event simulator or a continuous simulator, kind of like differential equations, or
I don't know. We looked at the equations. There are very many, because you have to do the heat transfer for everything. You got to put the occupancy schedule, how much you know about it. You got to put in what are the devices in it. You have to put the heating and the air conditioning. You put in the lighting. So each of these components would have a different equation.
Yeah, it's probably.
It's a massive,
stochastic, right?
massive system. It's like hundreds of pages. When you look at it, different equations. So I would assume some are differential, some are not. There's lots behind. But we only use the energy class. We didn't change anything. That's a commercial software that we can use. And we look at different scenarios. If we are merging it with the AI, how it's going to behave. So this is first just an illustration of the black is actual, and the two dashed are energy plus at deep learning. They're not following the pattern grade. It's just a fraction, just randomly taking these. But what we want to know is, if we merge the two, can we get the better results? We also want to know, if we are merging this, can we handle scenarios that the other two separately cannot? So the deep learning cannot handle no historical data, but energy plus can. So by merging the two, we're covering different scenarios. And I'll just go quickly over this one. So the first one is when both are available, energy plus and deep learning. So we are using, as deep learning, we are using LSTM. This PGMN, this is our new merged approach, and energy plus. You can see that PGMN is just slightly better than LSTM on its own. So if you have everything for the deep learning, merging doesn't give you a lot. If we have a part of the data that's missing, and with energy we can often have missing sensor information, if we have that scenario, our PGMN gets better than LSTM. And if we have no predictions from deep learning, we have only energy plus, we can still improve that learning by combining the two systems. And you can see that accuracy greatly differs. The best scenario is if we have historical data, then we can do really well. But we don't have that always. So this approach gives us flexibility to cover different scenarios. And maybe I'll just skip this one. This goes more into analysis of different components. Are they really contributing or not? So,
how do you intervene? So you want to do what if analysis and intervene, right? Do you intervene only on the energy class, or also on...
So the system stays the same. There is no change in the system. So if there is a no energy plus data, there's nothing is going to come here.
Yeah.
So the deep learning still goes through this.
Yeah, but I want to use this for what if analysis. Can I?
To use it for?
What if analysis. So one of the drawbacks of pure AI is that you can't intervene on the system.
We didn't test it for what if analysis. We tested for these like 5-6 scenarios. I think you could. It would need testing, because your what if scenario, deep learning wouldn't be, it's just historical data. So what if is not coming in. But this one, you could feed it, what if I change, I don't know, what if I install better lighting and see what happens.
Exactly.
We did not look into that. Would be a very good idea to look
Because this was the
into
motivation to involve.
It would be difficult to validate.
So you turn on
You
the
would
light
not-
on the weekends or something and see if this is correct.
Yeah, but it would be excellent to look into it for sure. So far we did talk about technical aspects, and we have more and more of these tools. Other people are doing it as well. But what do we really need for that real world impact? And I'll highlight a few main things. Government's equity trust in AI-enabled buildings. The building industry is heavily regulated. And anything in this space will probably need to be regulated in some way. So more and more, the AI influences cost, comfort, and so on. Decision affects everything. Lack of transparency could be a major issue, because we can't say, oh, AI told me it's going to be this much energy. We can't have that transparency with the AI. So the key governance challenge is the data ownership and consent. So federated learning is a step towards this, but it's not a complete. We need a firmer things about data ownership. Transparency and explainability. My research group does some explainability work. I've chosen not include it here, just too much. Accountability. If something goes wrong, if we are doing retrofit and AI gave us wrong information, how do we account for that? Interoperability across organization and jurisdictions. We got to think about equity as well. We have to make sure that by doing this, that it's not only a specific group of people benefiting from it. We somehow need to make it usable across the population. We want the community scale deployments. So our privacy preserving needs to be a default. Early in the design, we need to consider that, not, oh, we designed this, let's fix the privacy issues. Human in the loop, not automation only. There's more and more work with the AI and the human in the loop. And not only that gets the human input, but it also increases the trust because we have that human interaction. Interpretable models. The CAIS are interpretable models. I expect to see more on interpretability of CAIS, but they are relatively new, so it's just kind of coming up. And scalable, but local first deployments, respecting community needs. So we need something that can really scale easily. So for example, Energy Plus, we can't scale it to many buildings. It's just too time consuming. It takes days and days to do a single model. Looking forward, AI should be taken as enabler of something else, not replace anything. We don't want to replace the Energy Plus. We need to help the systems together. We need to be responsible how we affect the society, and that needs to be considered throughout the design process. When design responsibly, AI can help us lower carbon, improve resiliency, and equitable communities. So all these last few slides are looking forward to increase the impact. A lot of people are doing technology, but we don't want just technology. We want impact of this technology. And these are the directions we should be looking at that part. So this concludes my talk. Thank you.
Question about the Energy Plus. So this is a commercial, potentially, company that provides these models, right?
So Energy Plus is a software that a lot of building design companies use. It's a commercial software, so we had to
at some
pay.
point, they also had to gain trust, because these equations are also approximations, and we know that all models are wrong.
Yes.
But some are useful. So what is the difference between AI-based solution and this set of equations?
So
that
I
is also
agree.
an approximation.
I 100% agree. So with AI, people typically say it's a black box because we can't trace things through the system. So we can, when we have inputs and they are multiplied by weights, it's just a multiplication, so that can be traced. But once it gets to an activation function, then it kind of squishes different variables. So we can't really nicely trace it to the system. we can trace to the systems better with energy plus, but I don't think people are tracing. So that comes to your question. I personally think more it's about proving through the time that something is working consistently well in the different scenarios. And our work with when we do many different buildings, we want to prove this works. It's not just for this building, but if we repeat the process for many buildings, it still works. And I think, does the AI need explainability? Yes. But I think it needs time and proving consistently that it works. So yeah, theoretically, energy plus is explainable because we can trace it, but no, people don't do it. People just trust it. And ultimately, when you build a building and compare the actual versus energy plus, it's huge difference. The thing is, buildings are not built the way they're designed. Often when they build a building, things are tweaked and then they deviate from design. So to start with, they may not be exactly the same as original design. They may have been designed and the things were reduced to save the cost. Also, there are even just buying equipment. If you replace one HVAC with another HVAC, it's completely different what the building will use. So the errors they produce with actual are often very high. But yes, I think AI needs time to gain, and constant successes to gain trust.
So my follow-up would be, isn't it a good idea to start this kind of spin-off and try it on many buildings? Because in academia we're limited in resources. We cannot start trying it on a global scale unless the government supports it or local municipalities. But if there's a company that does it, that would be a great proof. So have your students considered doing something? Being the alternative to energy plus for you?
So, it would be, if you have the data, AI will beat the energy plus. The thing is, the whole civil engineering world, you better not tell them that these models are not giving great results. I have had my PhD student present something. It was actually, his work was this physics AI combination. And he said something like, physics, AI is consistently better than physics. You wouldn't believe discussion afterwards. Everybody was just around that one sentence. They didn't care about anything else. So the whole community believes in this approach. Does it do well in certain scenarios? Yes, it does. If you have all the information, it's going to give you reasonable numbers for the new building. AI can't do them. So I more think as the two things we either merge or we consider them both. I don't see them as one way or the other.
Thank you for the talk. I was just curious, I remember on one of the slides, I think it was part 2, you were showing that we're trying to predict approximately up to 16 hours ahead. Do you think it would be useful to predict further than that? Because I know you mentioned that it's very taxing and expensive.
Definitely. So this was the slide you're mentioning. So a lot of grid planning goes off the 24-hour ahead prediction. So in a night, they're doing this energy provisioning based on prediction for tomorrow. So therefore, the 24-hour ahead is extremely important. I don't know why we did 16 hours. Maybe in that paper, maybe we even had another one because I just pulled the example. So 24-hour ahead is very useful scenarios. If you go week ahead, is it useful? Yes, not as much as a 24-hour. We have way back, we have done predictions. So in London, there is this facility, they keep changing the name, but it's for big events like a hockey, basketball. I think it's called Budweiser Garden now. They change it every once in a while. So what they wanted is predict how much energy will an event take when they come to London. Because the way they operate is, let's say a concert wants to come to London, they ask the Budweiser gives them a price. So the top expense for Budweiser are people, the second top is energy. In the past, they had events where they lost money because their energy consumption went so high. So the band they practice ahead of time, and they're switching like hockey to, I don't know, concert. So they had these bands that they would come and practice few days ahead. And they would ramp up so much energy in these ahead of concert days and the concert day that the venue lost the money. So they wanted to do that prediction. So for that one we did, I don't remember, a year or two, because typically when event is coming, they ask a year or two ahead to kind of schedule, to book that venue. But this is specific for event. If this band comes and they're gonna do, I don't know, two days of practice and, I don't know, 3 concerts, they wanted to know what will the total be for that. So that is use case when it's more. So yes, going further can be. It works different when you go further, because you need to account with going only 24 hours. Tomorrow, the good chance is weather is similar to today. So it's much easier. If you look a year from now, weather is useless. You have season, yes. Variables are a little bit different. But yeah, it can be done. It has use case. Yeah. Any more questions? Okay. Thank you very much. Thank you.
Let's thank Katarina.